In the year 1774, a French chemist by name Antoine Lavoisier conducted an experiment. He took a piece of silvery, shiny metal called tin. He placed it in a vessel and sealed it on all sides and heated it to a high temperature. When you heat something to a high temperature in limited oxygen, it is called calcification. And during this experiment, he noticed that this silvery metal tin gradually disappeared, and in its place, a white powder gradually appeared. So, the substance he started with and the substance he ended up with are looking different. This is a silvery metal and this is a white powder. Not only that, they have different behaviors. Their chemical properties are also different. So obviously, this metal tin and this white powder, whatever it is, are two entirely different substances. And this process of calcification converted one kind of substance into a different kind of substance. And such a process or a change is called a chemical change. And Lavoisier weighed this vessel before the experiment, after the experiment, and several times during the experiment, and found its mass was the same every time. And he stated his observation in the form of a law called law of conservation of mass. That is, during a chemical change or a chemical reaction, there is no change in mass. That is, matter is neither created nor destroyed during a chemical change. The substance calcium carbonate is found in earth in many different forms. Chalk, marble, Iceland spar, etc. found in earth are different forms of the same substance, calcium carbonate. Another French chemist by name Joseph Proust studied calcium carbonate found in different forms in the earth. And he noticed that no matter in what form this substance is present, it is always composed of three elements: calcium, carbon, and oxygen. Secondly, the proportions of these elements by weight is found to be a constant. That is, if you take 100 grams of calcium carbonate present in the form of chalk or marble or Iceland spar or some other form, it always contains 40 grams of calcium, 12 grams of carbon, and 48 grams of oxygen. These three elements and in this proportion. Based on this observation, he suggested another law called law of constant composition or law of definite proportions. And this law states the ratio of the masses of different elements in a compound is constant. And this law is applicable to all compounds, not just calcium carbonate. Let us take another example. Take samples of water from different sources: rainwater, distilled water, water from a nearby lake, water from a famous river. No matter where you get a sample of water from, if you pass electricity through it, we observe that it always breaks into only two elements: hydrogen and oxygen. And if you collect the hydrogen and oxygen produced and weigh them, you will always find that for one part of hydrogen, there are always 8 parts of oxygen by weight. This is the proportion in which hydrogen and oxygen are present in water by weight. And this is what is called composition of water by weight, that is 1 to 8. This means two things. The first thing is, to make water, we always need two elements, hydrogen and oxygen. If you say hydrogen is not available in the market, can we manage with some nitrogen just for this time? No, it will not work. To make water, we always need hydrogen and oxygen. No other combination of elements would produce water. Secondly, to make 180 grams of water, we always have to combine 20 grams of hydrogen with 160 grams of oxygen. See, the total mass of hydrogen and oxygen put together is 180, and the mass of water produced is also 180. So law of conservation of mass is satisfied, and the ratio of these two masses is 1 to 8, and this is the composition of water by weight approximately. So law of constant composition is also satisfied. Now, what would happen if we mixed 40 grams of hydrogen with 140 grams of oxygen? Do we get 180 grams of water? No, we will get less than 180 grams of water, because for 160 grams of oxygen we need 20 grams of hydrogen. Here we took less than 160 grams of oxygen, but more than 20 grams of hydrogen. So we have excess hydrogen. So there will be some hydrogen left over at the end of the reaction, and the amount of water we would get is less than 180 grams. Similarly, what would happen if we combine 10 grams of hydrogen with 170 grams of oxygen? Same, this time we have excess oxygen. There will be some leftover oxygen at the end of the reaction, and the mass of water produced will be less than 180 grams. So that means to produce 180 grams of water, only this combination would work for the weights of hydrogen and oxygen. No other combination will produce 180 grams of water. So nature is very strict or rigid when it came to the composition of water. For that matter, the composition of any compound. Why? So why the recipe of water is fixed, whereas we can change the recipe of a tomato soup as we wish? Assuming there is no loss in mass, in the making of this soup, we can mix 20 grams of onions with 160 grams of tomatoes to make 180 grams of soup, or we can use these amounts of onions and tomatoes, or these amounts, or any other combination of amounts that add up to 180 grams would work. Literally, we have infinite possibilities. So we have infinite freedom to change the recipe of this soup, whereas we have zero freedom to change the recipe of water. Why? Well, one may say that water is a compound of hydrogen and oxygen, and because the composition of water is fixed, you cannot change it. Whereas This soup is a physical mixture of onions and tomatoes because you can mix things in any proportions you want to make the mixture. You have the freedom here. That's not at all an answer to our question. It's like saying that is how compounds are, this is how mixtures are, so just accept it. Our question is why we have the freedom to change the recipe of the soup and no freedom at all to change the recipe of a compound. See, we don't have to ask anyone. We can think through it ourselves. What we are saying here is we can mix any quantity of onions with any quantity of tomatoes to make the soup. But to be able to mix them in any quantities, we must be able to obtain them in any quantities, right? So the question is, can we obtain any amount of tomatoes? 1 kilogram, 1.5 kilograms, 2 kilogram, 3 kilogram? Yes, you can obtain tomatoes in any quantity that you want. That is because tomatoes come in different sizes. By using a combination of tomatoes with different masses, we are able to add up their mass to the required quantity. That is how we are able to buy tomatoes in different quantities. Same with onions. Now imagine that all tomatoes in this world are identical, each with a mass of 70 grams. Now, if I buy one tomato, I would have 70 grams of tomatoes. If I buy two tomatoes, I would have 140 grams, or 210 grams, or 280 grams, and so on. I will not be able to buy an amount that is between 70 and 40 grams because the vegetable vendor would not let me cut a tomato, and all tomatoes are identical, 70 grams each. So I suddenly lost the freedom to buy any amount of tomatoes that I want if I imagine all tomatoes in this world are identical. Then you may say, though the shopkeeper doesn't let you cut them, you can cut them after bringing them home. So if you want 150 grams of tomatoes, you can still get it. Buy 3 tomatoes, then you would have 210 grams of tomatoes with you. So take 2 tomatoes, that would be 140 grams. You need 10 more grams of tomatoes. So cut the third one so that you get a piece of 10 grams and mix them to get 150 grams of tomatoes. So though I am not able to buy 150 grams of tomatoes, I am still able to obtain 150 grams of tomatoes because a tomato is cuttable. So that is giving me some freedom, though I lost some freedom when I assumed that all tomatoes are identical. Now let us assume that a tomato is uncuttable. Then I lost this freedom as well. Then there is no way I can ever obtain 150 grams of tomatoes because all the tomatoes in this world are identical, each with a mass of 70 grams, and tomatoes are uncuttable. So I can have only 70 grams or 140 grams or 210 grams or 280 grams and so on. So suddenly I totally lost the freedom to obtain any amount of tomatoes that I want if all tomatoes in this world are identical and they are uncuttable. Now let us impose similar restrictions on onions as well. Say all onions are identical and uncuttable, each with a mass of 40 grams. Then we can have either 40 grams of onions, 80 grams, 120 grams, 160 grams, and so on. Nothing in between is possible. But still, there are infinite number of combinations for the amounts of tomatoes and onions in which they can be mixed. See, I can mix 70 grams of tomatoes with 40 grams of onions, or 80 grams, or 120 grams, or 160 grams, and so on. Now let us impose an interesting restriction. Let us limit the capacity of an onion for tomatoes and the vice versa. That is, say, one onion can mix only with 4 tomatoes. Not a bit more, not a bit less. Now, what happens? Because of this restriction, if you mix one onion with 5 tomatoes, then only 4 of them would mix with this onion, and the 5th one will be left behind in some corner of the pan, because the capacity of one onion for tomatoes is 4. What would happen if we mix one onion with only 3 tomatoes? Then they refuse to mix altogether. You can stir them as long as you want in the pan, but nothing happens, because an onion requires 4 tomatoes to mix. If it is less than 4, they would not mix at all. Now let us make some tomato soup with these restrictions. We said for 1 onion, 4 tomatoes. If you take 2 onions, 8 tomatoes, 3 onions, 12 tomatoes, and so on. We said the mass of an onion is 40 grams and mass of a tomato is 70 grams. So 4 times 70 grams. Here 2 times 40 grams of onions, 8 times 70 grams of tomatoes. 3 times 40 grams of onions, 12 times 70 grams of tomatoes. Now, if you look at the ratio of their weights, 40 grams to 4 times 70 grams, 2 times 40 grams to 8 times 70 grams, 3 times 40 grams to 12 times 70 grams. Now these units get cancelled, these zeros get cancelled. Here the ratio is, these 4s also get cancelled, the ratio is 1 to 7. Here these zeros get cancelled, these units get cancelled. 4 2s are 8. So this 8 and this 8 get cancelled. Again it is 1 to 7. And the zeros get cancelled, units get cancelled. 3 4s are 12 and 12 here. So these two get cancelled as well. So again the ratio is 1 to 7. So the composition of the soup is now a constant. So by applying 3 restrictions on tomatoes and onions, we made the composition of soup a constant. So that means by using more onions and tomatoes, we are only making more and more amount of that soup, but we are not changing its composition. So all these soups taste identical, and that would be really boring. But by imposing those 3 restrictions, we are successful in making the composition of this soup constant or fixed. Now what can we say about hydrogen and oxygen that water is composed of? Because the composition of water is also a constant. That means nature imposed the same restrictions on hydrogen and oxygen that we imposed on tomatoes and onions to make the composition of this soup a constant. So this is what the law of constant composition was trying to tell us. Though Joseph Proust could not understand what this meant, an English chemist by name John Dalton understood it. And based on this, he proposed a theory called Dalton's atomic theory. And we shall discuss that in a moment. Okay, what are the three restrictions we applied on tomatoes and onions to make the composition of this soup a constant? The first one is tomatoes are all identical. They all come in a single size with a single mass. They are not allowed to have different sizes and different masses. And the same with onions. Secondly, tomatoes are uncuttable. You cannot cut a tomato into smaller pieces. And most importantly, we have fixed the capacity of tomatoes for onions and the vice versa. And remember, to make the composition of this soup a constant, we need all these three restrictions. If you drop even a single restriction, the composition of the soup will not be a constant. Think about it. I will leave it as an exercise for you. And these are three of the first four postulates of Dalton's atomic theory proposed in 1808. We have to replace tomatoes and onions with elements. And the first postulate of Dalton's atomic theory is matter, everything that is around us, including us, is composed of tiny indivisible particles ultimately. Because these particles are indivisible or uncuttable, they are called atoms. Because in Greek, atomos means uncuttable. Secondly, atoms of a given element are all identical. They have the same mass and size, etc. So, the hydrogen gas present in a container is composed of identical hydrogen atoms according to Dalton. And oxygen gas present in a container is also composed of identical oxygen atoms. But atoms of hydrogen are different from atoms of oxygen. A hydrogen atom and an oxygen atom have different masses and different sizes. Otherwise, we cannot explain different elements and substances that we see around us. And the fourth postulate is atoms combine in fixed and simple whole number ratios. Okay, we shall discuss this postulate after discussing this last one. See, according to Dalton, atoms are indestructible. We simply cannot get rid of atoms. Atoms are forever. And according to law of conservation of mass, matter is neither created nor destroyed during a chemical change. So when hydrogen explodes in oxygen to form water vapor, the total mass of hydrogen and oxygen that are combining with one another must be equal to the total mass of water vapor produced. So there is no gain or loss of mass in this change. And according to Dalton, this hydrogen is composed of atoms and this oxygen is also composed of atoms. Because atoms are indestructible and matter is neither created nor destroyed during a chemical change, it means atoms are neither created nor destroyed during a chemical change. That means atoms are conserved during a chemical change. The total number of atoms before the change must be equal to the total number of atoms after the change. We also know that atoms cannot be transformed either. We cannot change an iron atom into a gold atom. We wish, but we cannot. Similarly, we cannot transform a hydrogen atom into an oxygen atom and the vice versa. That means atoms of each element are conserved during a chemical change. That is, the total number of hydrogen atoms before the change must be equal to the total number of hydrogen atoms after the change, and the same with oxygen atoms. So, atoms are conserved in a chemical change. More precisely, atoms of each element are conserved in a chemical change. But if all the atoms that are present before the change are also present after the change, then what is going on in a chemical change? How this hydrogen and oxygen are getting converted into water vapor? What is going on when wood burns in air to form ash plus some gases? If all the atoms present before the combustion are also present after the combustion, what is going on? See, a chemical change is regrouping or rearrangement of atoms. When hydrogen reacts with oxygen, it is the atoms of hydrogen that combine with atoms of oxygen to form what John Dalton called as compound atoms of water vapor. That is what a chemical change is. Chemical change is an interaction between atoms in which they combine with one another to form different substances. So, in this reaction, certain number of hydrogen atoms combine with certain number of oxygen atoms to form each compound atom of water vapor. And the number of atoms of different elements present in one compound atom of any substance is called its atomic composition. But my question is, can I keep changing the atomic composition of a compound atom of water? That is, can I attach 5 hydrogen atoms to 6 oxygen atoms to form one compound atom of water, and to make another compound atom of water 7 hydrogen atoms to 11 oxygen atoms, and so on? Can I keep changing its atomic composition? The answer is no. If you could, then the composition of water will not be a constant. Remember, the third restriction we imposed on tomatoes and onions to make the composition of the soup a constant? We fixed the capacity of tomatoes for onions and the vice versa. We said if we drop this postulate, then the composition of the soup will not be a constant. Similarly, because the composition of water is a constant, it means the capacity of hydrogen atoms for oxygen atoms is fixed and the vice versa. That means we cannot change atomic composition of water. Every water molecule in this universe has the same atomic composition. Whatever it is, we don't know if it is 5 to 6, 7 to 11, 1 to 1, 2 to 1, 33 to 54. We don't know what that composition is, but whatever it is fixed. So, this part of the fourth postulate came directly out of law of constant composition. It says atoms combine in fixed whole number ratios to form compound atoms. Now the million-dollar question is, where did this word simple come from? We understand that because the composition of a compound is fixed, atoms combine in fixed whole number ratios. But why should these ratios be simple? See, if we take the atomic composition of compound atom of water, it could be 1 to 1 or 1 to 2 or 2 to 1 or 1 to 3 or 3 to 1 or 3 to 2 or 2 to 3 or 1 to 4 or 77 to 19 or 7 to 18 or 3 to 19 or some other ratio. And these are simple whole number ratios and these are not. And if the atomic composition of a compound atom of water found in Pacific Ocean is this, then this is the atomic composition of every other compound atom of water found in this universe. That is what we mean by fixed. But John Dalton says it is not only fixed, it must also be a simple whole number ratio. That is, he is ruling out these possibilities. He says it is one of these or something similar to these. It is not only fixed, it is also simple. But the constant composition of a compound does not mean that it is a simple ratio. It only means its composition or atomic composition is fixed. Then how did John Dalton know that it is a simple whole number ratio? He simply assumed it. And he not only assumed that these ratios must be simple, he went ahead and assumed what that ratio must be for each reaction. For this reaction between hydrogen and oxygen, he assumed that one hydrogen atom combines with one oxygen atom in the formation of a compound atom of water. So here he said the ratio is 1 to 1. Absolutely no evidence for this. Same here for the reaction between hydrogen and nitrogen. He said it is 1 to 1. Same for the reaction between nitrogen and oxygen. And when two elements combine to form more than one compound, like carbon and oxygen, in one case he assumed that one carbon atom combines with one oxygen atom, and in the second case he assumed that one carbon atom combines with two oxygen atoms. All this without a shred of evidence. Here comes the interesting part. Let us say the mass of a carbon atom is x grams and the mass of an oxygen atom is y grams. So in this reaction, x grams of carbon combines with y grams of oxygen to form a compound atom of this oxide. Because all carbon atoms are identical, the mass of this carbon atom is also x grams. Because all oxygen atoms are also identical, If the mass of one oxygen atom is y grams, the mass of two oxygen atoms would be 2y grams. So in this reaction, x grams of carbon combines with 2y grams of oxygen to form a compound atom of this oxide. In both the reactions, the mass of carbon is same, but the masses of oxygen are different. If you take the ratio between different masses of oxygen that are combining with the same x grams of carbon in these two reactions, it is y grams to 2y grams. These units get cancelled, these y's get cancelled, and the ratio is 1 to 2. And this is a simple whole number ratio. By the way, what is this ratio? It is the ratio between different masses of one element that are combining with the same mass of a second element in the formation of different compounds. And it is a simple whole number ratio. And John Dalton proposed this in the form of a law called law of multiple proportions. And here is the statement of law of multiple proportions. If two elements combine to form more than one compound, then the masses of one element that combine with a fixed mass of the second element are in simple whole number ratios. So John Dalton predicted this law based on his theory and his assumption that atoms combine in simple whole number ratios. And after it was predicted, people verified their experimental data and found that it is in fact true. Because the law of multiple proportions is experimentally verified, that John Dalton originally predicted based on the assumption that atoms combine in simple whole number ratios, means that John Dalton's assumption is in fact right. So, law of multiple proportions supports the idea of Dalton that atoms combine in simple whole number ratios. But we still have a problem with these particular ratios that John Dalton assumed, because law of multiple proportions says that the ratios must be simple, but it does not tell you what that ratio exactly is in each reaction. In this case, Dalton assumed that it is 1 to 1, but it could be any other simple whole number ratio. It could be 1 to 2 here, and instead of 1 to 2 as assumed by John Dalton, it could be 1 to 4 here. So, law of multiple proportion only says that these ratios must be simple, but it does not tell you what it exactly is. But John Dalton made these wild assumptions that in this case it is 1 to 1 and in this case it is 1 to 2. There is no evidence for this. Let me make it very clear. Law of multiple proportions talks about the ratio between these masses, and for these masses to be in simple whole number ratios, the ratios between these atoms must be simple whole number ratios. So if this ratio is not a simple whole number ratio and it is something like 5 to 17 and this is 5 to 33, then the ratio between these masses would be 17 to 33. This will not be a simple whole number ratio. That is what I am trying to explain here. So obviously John Dalton could not explain his assumptions about these ratios. He simply made these assumptions. They could be right, they could be wrong. But using these assumptions, John Dalton did something interesting. As we discussed previously, in the reaction between hydrogen and oxygen in the formation of water, he assumed that one atom of hydrogen combines with one atom of oxygen to form one compound atom of water. That is, in one compound atom of water, there is only one hydrogen atom and one oxygen atom according to John Dalton. So its atomic composition is 1:1. And he experimentally measured the weights of hydrogen and oxygen that completely combined with one another without any leftovers. And he found these weights to be in the ratio of 1:7. The weights of different elements that completely combine with one another without any leftovers are known as combining weights. So he found the combining weights of hydrogen and oxygen in this reaction to be in the ratio of 1:7. Obviously, this is wrong. Today we know that it is approximately 1:8. But the measurement techniques back then were not very refined, so he found it to be 1:7. So this is the composition of water by weight according to Dalton, and this is the composition of a compound atom of water according to Dalton. Now, if equal number of hydrogen and oxygen atoms are combining to form one compound atom of water, and if 1 gram of hydrogen is completely combining with 7 grams of oxygen without any leftovers, that only means there are an equal number of hydrogen and oxygen atoms in these amounts of hydrogen and oxygen. So if there are n hydrogen atoms in 1 gram of hydrogen, there must be n oxygen atoms in 7 grams of oxygen. So the total weight of n identical oxygen atoms is 7 grams, and the total weight of n identical hydrogen atoms is 1 gram. Here MO is the mass of one oxygen atom, MH is the mass of one hydrogen atom. Let us call this equation 1 and this 2. If you divide 1 with 2, these n's get cancelled, these units get cancelled. On the left hand side we will have MO over MH, and on the right hand side we will have 7 over 1. And if you cross multiply, MO will be 7 times MH. This is interesting. We have seen a similar equation before. Do you remember this equation? Mass of the bag of oranges is 5 times mass of the platinum iridium cylinder. There, the mass of this platinum iridium cylinder was taken as the reference for measuring mass. Similarly, if we take the mass of a hydrogen atom as reference for measuring masses of other atoms, then an oxygen atom is 7 times as heavier as a hydrogen atom. And if you call mass of one hydrogen atom as 1 AMUH, I just made up some name. Just like we called the mass of this platinum iridium cylinder as 1 kilogram, then the mass of an oxygen atom would be 7 times 1 AMUH or 7 AMUH. And if you take MH to the left hand side, then MO over MH will be 7, a number with nothing next to it. And John Dalton called this ratio atomic weight. So atomic weight is the ratio between the mass of one atom of any element in general and the mass of one hydrogen atom, that is taken as the reference for measuring masses of atoms. And as you can see, this is a ratio between two masses, so this is a dimensionless number. So atomic weight is the relative mass of an atom. Mass of an atom relative to the mass of the hydrogen atom, that was taken as reference by John Dalton. So now we have a way to weigh atoms using mass of a hydrogen atom as reference. And here is the definition of atomic weight of an element. It is the ratio between these two. And if you want to know the mass of one atom of an element, you have to multiply this with this. So it is the atomic weight of the element, which is a number, multiplied by mass of one atom of hydrogen. Remember, this term represents the physical quantity called mass. And when you multiply it with a number, again you will get the same physical quantity mass. That is why this product is called mass of one atom of an element, because we are treating this term as a representation of the physical quantity called mass. And there is another name for mass of one atom, that is atomic mass. So atomic mass is another way of saying mass of one atom. So atomic mass of an element is equal to its atomic weight multiplied by atomic mass of hydrogen. And we said atomic mass of hydrogen is 1 AMUH, just a name we made up. So atomic mass of an element is atomic weight of the element in AMUH. Again, pay attention to these two closely related names. Atomic weight is a dimensionless number. It is a ratio between two masses. It tells the number of times an atom of an element is heavier than an atom of hydrogen. Whereas atomic mass represents the physical quantity called mass of an atom, and it is expressed in units of mass, and they are not the same. Atomic weight is not a physical quantity, it is just a number, whereas atomic mass is a physical quantity. By the way, what will be the atomic weight of hydrogen? It is the ratio between mass of one atom of hydrogen and the mass of one atom of hydrogen. So numerator and denominator are equal, they get cancelled, and the atomic weight of hydrogen is 1. That is by definition. This is just another way of saying that the mass of one hydrogen atom was taken as the reference. And in this fashion, Dalton determined the atomic weights of many elements. And looking at them, we can say that they are horribly wrong. They are wrong for two reasons. His assumptions about the atomic compositions of different compound atoms were wrong, and his measurements were not accurate. But he figured out a way to measure the masses of atoms using the mass of a hydrogen atom as reference. And when Dalton measured the masses of elements that completely combined with one another, a French chemist by name Joseph Gay-Lussac measured the volumes of different gases that completely combined with one another if all the reactants are gases. And the volumes of gases that completely combined with one another without any leftovers are known as combining volumes. So for this reaction, Gay-Lussac found the combining volumes of hydrogen and oxygen are in the ratio of 2:1. And for this reaction, he found them to be in the ratio of 3:1. And for this reaction, according to him, they are in the ratio of 1:1. Remember, these are all gases: hydrogen, oxygen, nitrogen, etc. and obviously these are simple whole number ratios. And moreover, if there are any gaseous products formed in that reaction, then the volumes of the gaseous products are also in simple whole number ratios with the volumes of the reactants that combined with one another. See, in this case, the ratio becomes 2 to 1 to 2. Again 3 to 1 to 2 because 2 liters of ammonia is produced here. And in this case, 2 liters of nitric oxide is produced. So the ratio becomes 1 to 1 to 2. And he stated this in the form of a law called law of combining volumes of gases. Remember, this law is applicable only if all the reactants are gases. And it states that at constant temperature and pressure, the ratios of combining volumes of gases are in simple whole number ratios. See, volumes of gases are highly sensitive to temperature and pressure. A slight change in temperature or pressure will produce a huge change in the volume of a gas. So, volumes of gases must be compared at the same temperature and pressure. And the most important word in this statement is this: simple. We came across this word before. Remember Dalton's theory? He says atoms combine in fixed and simple whole number ratios. And he assumed some arbitrary ratios for different reactions without providing any evidence. But Gay-Lussac says, look at my combining volumes. The combining volumes are in simple whole number ratios. Maybe these ratios are trying to tell us something. Maybe this is the ratio in which hydrogen atoms and oxygen atoms combine to form one compound atom of water. So according to Gay-Lussac, the atomic composition of a compound atom of water is 2 to 1. That is, in one compound atom of water, there are 2 hydrogen atoms and 1 oxygen atom. Because the combining volumes of hydrogen and oxygen in the formation of water are in the ratio of 2 to 1. So what Gay-Lussac is saying is the ratio of the combining volumes of the gases is equal to its atomic composition or the composition of the product formed in that reaction. Similarly, in one ammonia compound atom, he says there are 3 hydrogen atoms and 1 nitrogen atom because the combining volumes of hydrogen and nitrogen are in the ratio of 3 to 1. So the atomic composition of ammonia is also 3 to 1. Similarly, the atomic composition of nitric oxide is 1 to 1 according to Gay-Lussac because the combining volumes of nitrogen and oxygen in the formation of nitric oxide are in the ratio of 1 to 1. This ratio of combining volumes is equal to the atomic composition of the compound atom formed. And John Dalton was too stubborn to accept the argument of Gay-Lussac. He simply rejected the idea of Gay-Lussac. But we know Gay-Lussac was right, at least in these cases. See, here these ratios are equal. The ratios between the combining volumes and the atomic compositions are the same in each case. Because we know Gay-Lussac is right, let us try to recalculate the atomic weight of oxygen using the atomic composition suggested by Gay-Lussac. According to Dalton, 1 gram of hydrogen completely combines with 7 grams of oxygen. According to Gay-Lussac, 2 liters of hydrogen completely combines with 1 liter of oxygen. And Gay-Lussac suggested that the ratio of the combining volumes and the ratio of the number of atoms combining to form one compound atom are the same. So because the combining volumes are in this ratio, Gay-Lussac says it is 2 hydrogen atoms that are actually combining with 1 oxygen atom to form one compound atom of water. That is, the atomic composition of water is 2 to 1, not 1 to 1 as assumed by John Dalton. So that means each oxygen atom combines with double the number of hydrogen atoms to form one compound atom of water. So if there are n oxygen atoms in 7 grams of oxygen, then there must be double the number of hydrogen atoms in 1 gram of hydrogen, obviously. Then the total mass of n identical oxygen atoms is 7 grams and the total mass of 2n identical hydrogen atoms is 1 gram. Again, if you divide 1 with 2, these n's get cancelled, these units get cancelled. Finally, we will have MO over MH equals to 14. And by definition, this is the atomic weight of oxygen. Wow! In one step, we corrected the atomic weight of oxygen from 7 to 14 just by fixing the atomic composition of water. So, thanks to Gay-Lussac. But this is still not the correct atomic weight of oxygen. In 1895, an American chemist by name Morley determined the most accurate atomic weight of oxygen using the mass of a hydrogen atom as reference, and it is 15.879. So obviously it took us many decades to go from these inaccurate atomic weights to these more accurate atomic weights. That's mainly because it took us a lot of time to improve the measurement techniques. As and when the techniques got improved, the atomic weights got revised. Now let us take a look at these two lines numbered 2 and 4. This line says 2 liters of hydrogen combines with 1 liter of oxygen. This line says 2n hydrogen atoms combine with n oxygen atoms. That only means in 2 liters of hydrogen, there are 2n hydrogen atoms. In 1 liter of oxygen, there are n oxygen atoms. Then, how many hydrogen atoms will be there in 1 liter of hydrogen? If 2 liters has 2n hydrogen atoms, then 1 liter of hydrogen will have n hydrogen atoms. If you halve the volume, then the number of atoms would also get halved. Now you look at these two volumes, 1 liter of hydrogen and 1 liter of oxygen, n hydrogen atoms and n oxygen atoms. That is interesting, right? So, an interesting observation came out of this. It says equal volumes of gases at the same temperature and pressure contain equal number of atoms. So if you try to combine Dalton's atomic theory and Gay-Lussac's law or his argument, then it leads to this conclusion that equal volumes of gases at the same temperature and pressure contain equal number of atoms. But to an Italian chemist by name Avogadro, there is a small problem with this observation. Why Avogadro was not quite happy with this observation? Let us see. 2 liters of hydrogen combines with 1 liter of oxygen to form 2 liters of water vapor. Remember, this observation must be applied to all atoms, not only to atoms of elements. It applies even to compound atoms. And if equal volumes have equal number of atoms, and if there are n oxygen atoms in 1 liter of oxygen, obviously in 2 liters of hydrogen there must be 2n hydrogen atoms, right? The volume is doubled, so the number of atoms must also get doubled. Same here. In 2 liters of water vapor, there must be 2n compound atoms of water vapor. If you divide all the terms with 2n, 2n over 2n is 1, n over 2n is half, 2n over 2n is 1. Now read this line. It says, one hydrogen atom combines with half oxygen atom to form one compound atom of water vapor. That means to make one compound atom of water vapor, you have to cut an oxygen atom. That means you have to violate Dalton's atomic theory. Dalton says atoms are uncuttable. So, if Gay-Lussac's argument is correct, then Dalton's atomic theory is wrong. If Dalton's theory is correct, then this observation has some problem. But Dalton's atomic theory is correct because there was a lot of evidence to support that theory and everyone liked it. So there is some difficulty between this observation and Dalton's atomic theory. And to remove this difficulty, Avogadro for the first time introduced the idea of molecules. A molecule is an independent, stable group of atoms. A molecule is a bunch of atoms that are glued to one another. Because a molecule is a group of atoms, it can be cut into atoms if required. Molecules are divisible. So let us replace the word atom with molecule wherever it is in this line. Now it reads, 2n hydrogen molecules combine with n oxygen molecules to produce 2n molecules of water vapor. Again divide all the terms with 2n. 2n over 2n is 1, n over 2n is half, 2n over 2n is again 1. Now read this line. It says, one hydrogen molecule combines with half oxygen molecule to produce one molecule of water vapor. And molecules are divisible. We do not violate Dalton's theory when we cut a molecule into atoms. So no problem with this line. So Avogadro cleverly resolved the incompatibility between Dalton's atomic theory and the argument that came out of Gay-Lussac's law by using the idea of molecules. So, according to Avogadro, equal volumes of gases at the same temperature and pressure contain equal number of molecules, not atoms. And he stated it in the form of a hypothesis called Avogadro's hypothesis. It says, at the same temperature and pressure, equal volumes of all gases contain equal number of molecules, not atoms. So, what Avogadro says is, Dalton is right when he said an atom is indivisible, but he is wrong when he said hydrogen gas is composed of separate individual hydrogen atoms. According to Avogadro, hydrogen gas is composed of hydrogen molecules, and each molecule of hydrogen contains two or more hydrogen atoms. he did not know how many hydrogen atoms are there in each molecule of hydrogen. So, this was the picture of hydrogen gas given by Dalton, and this was given by Avogadro. If hydrogen is composed of hydrogen molecules, what about other substances? Is everything out there composed of molecules? No. We know what elements and compounds are. Of all the elements that we know, these are the only elements that contain separate independent groups of atoms called molecules. No other element contains separate independent groups of atoms called molecules. And the number of atoms present in one molecule of an element is called atomicity. Today, we know molecules of these elements contain 2 atoms each. That is why they are called diatomic molecules. A molecule of phosphorus contains 4 atoms, so it is tetraatomic. Molecules of selenium and sulfur contain 8 atoms each. That is why they are octaatomic. And we know oxygen exists in another form called ozone. And in a molecule of ozone, there are 3 oxygen atoms. That is why it is triatomic. No other element contains molecules, metals, inert gases, etc. Okay, what about compounds? See, there are many compounds like carbon dioxide, methane, etc. that are composed of separate molecules. But there are compounds like sodium chloride that are not composed of molecules. They are composed of ions. Ions are electrically charged particles. In these compounds, a large number of ions, oppositely charged ions, are arranged in a giant network. And the smallest part of that arrangement or network is called a unit. And because these compounds are composed of ions, they are called ionic compounds. And ionic compounds do not contain molecules. And ionic compounds like sodium chloride, sodium sulfate are soluble in water. That is, they can be mixed with water homogeneously. And when they are dissolved in water, this entire structure falls apart. That is, these ions get separated from one another and start moving freely. They are held tightly in their position only when they are in the form of crystals. So slowly our understanding about what matter is composed of is getting better. Dalton said elements are composed of atoms. Then Avogadro said, no, some elements are composed of molecules. Today we know there are many compounds that are composed of molecules and many compounds that are composed of ions. So the gold ring that you wear is composed of gold atoms. The oxygen that we breathe is composed of molecules. The sugar we eat is composed of molecules. The salt that we eat, common salt, is composed of ions. And when it is dissolved in water, the ions are getting separated from one another. So far we spoke about 4 different things: atoms, molecules, the smallest unit of an ionic compound, and ions. Here are some elements that are composed of atoms, and they are represented by using their symbols. Here are some examples of substances that are composed of molecules. Substances that are composed of molecules are known as molecular substances, whether it is an element or a compound. And molecules of a substance are represented by its molecular formula. This is the molecular formula of oxygen. This is the molecular formula of methane, and so on. In case of ionic compounds, there are no molecules. So the formula we use to represent an ionic compound represents the smallest unit of that compound. not a molecule. That is why this is called formula unit. Remember, ionic compounds do not have molecules. And ions are represented by using their formulae. And we have to show the charge on the ion as a superscript. Just the way we defined atomic weight for atoms, we can define molecular weight for molecules, formula weight for formula units, ionic weight for ions. Molecular weight is the number of times a molecule of the substance is heavier than a hydrogen atom. Formula weight is the number of times a formula unit is heavier than a hydrogen atom. Ionic weight is the number of times an ion is heavier than a hydrogen atom. And mass of one atom is known as atomic mass, right? Similarly, mass of one molecule is called molecular mass. And to get molecular mass, we have to multiply its molecular weight with the mass of one hydrogen atom. And we called it 1 AMUH. So, if you express molecular weight in AMUH, you will get molecular mass of the substance. Similarly, mass of one formula unit is called formula mass. And formula weight expressed in AMUH is its formula mass. Similarly, mass of one ion is called ionic mass. Again, to get ionic mass, you have to express its ionic weight in AMUH or multiply these two. We have used mass of one hydrogen atom as the reference for atomic weights for many decades, but there were many problems with hydrogen standard. I have listed those problems here, but we can discuss them separately if you are interested. Then you may ask, why did Dalton take it as the reference in the first place? Atomic weight is the ratio between these two masses, and hydrogen atom is the lightest of all atoms. Therefore, for any element, the value of the numerator will be greater than the value of the denominator. So, atomic weights of all elements will be greater than 1, and for hydrogen it will be equal to 1, obviously. And numbers greater than 1 are convenient to us. So, mass of hydrogen atom was a convenient and good choice for atomic weights. But there were many practical problems with hydrogen standard. Finally, they switched to the oxygen standard. And oxygen standard solved many of these practical problems. Now, how do we define atomic weight on the oxygen scale? On the hydrogen scale, atomic weight is the ratio between the mass of one atom of the element and mass of one hydrogen atom. Here we took the entire mass of a hydrogen atom as the reference. Should we do something similar on the oxygen scale? Should we take the entire mass of one oxygen atom as the new reference for atomic weights? We can certainly do that. Nothing wrong with it. But an oxygen atom is 15.879 times heavier than a hydrogen atom. Therefore, the value of the denominator in this fraction will be much higher than the value of the denominator in this fraction for the same numerator, that is, for the same element. That means the atomic weights on the new oxygen scale would be much smaller than the atomic weights on the hydrogen scale they were using back then. So, if you take the entire mass of an oxygen atom as the new standard, the atomic weights would change drastically. Atomic weights are used by students, teachers, research work, industry, and so on. And if you change atomic weights drastically, everyone will get confused. Therefore, we understand that there is a good reason to change from hydrogen to oxygen. But in doing so, make sure that atomic weights are not changed drastically. So that only means these two denominators must also be same. How can we make these two denominators equal? See here, mass of one hydrogen atom is equal to 1 over 15.879 times mass of one oxygen atom. This is what we have here and this is what we have here. So to make them equal, we have to multiply this term with 1 over 15.879. So if we take 1 over 15.879 times mass of one oxygen atom as the new standard on the oxygen scale, then the atomic weights on the new oxygen scale will be very close to the atomic weights on the previous hydrogen scale. But instead of taking 1 over 15.879 times mass of one oxygen atom as the reference, they took 1 over 16 times mass of one oxygen atom as the reference. They rounded this number to 16. That was because when they rounded it off to 16, they found that for many elements, the atomic weights were very close to whole numbers. Not for all elements, but for many elements. And numbers close to whole numbers are very convenient to us. That is why instead of taking 1 over 15.879 here, they took 1 over 16. So on the new oxygen scale, mass of one oxygen atom is taken as 16 units. And they gave a name to this unit. It is called atomic mass unit, abbreviated as AMU. Obviously, one AMU will be 1/16th of mass of an oxygen atom, and this is the new standard or reference. And atomic weight of oxygen would obviously be 16 without this unit. That is how a new oxygen scale of atomic weight was started.